technique I knew was to print out all the assembly code and try to read it and understand it all, and that is heroic. But I then took a class from a European group called the HoneyNet Alliance, and they showed me very good tools that make it much easier to analyze malware. And it first occurred to me, this is maybe 5 years ago, that it might be possible to teach a class in this stuff. But the problem is their class used real malware, which is the same thing SANS classes do. And they can do that, but I cannot do that at a public university, community college with students who cannot really, I can't have people handling real malware because they'll lose it and we'll all get in trouble. And this book comes with a bunch of fake malware to analyze, which is relatively harmless, by which I mean it doesn't break systems and it does not spread, but it does sort of foul them up and is annoying and it's hard to remove. So you don't want to run it on your main machine, but if you run it on a virtual machine, it's safe enough to use. And it's designed to mimic all the behavior of real malware. So you can run it in any Windows machine you like, but what I recommend is using this machine you can download here, which is a Windows 2008 machine I made that has all the tools already installed. Because we're going to use a lot of different tools and they're pretty irritating to set up. A lot of them require special batch launchers and such. Different tools and they're pretty irritating to set up. We're getting a lot of them require special batch. I think somebody's got their speakers on. I can probably, hey, Cheerio, you can probably mute. I probably can't because I'm not the host, but what I usually have to do is mute my students when I'm using Zoom because of that. Oh, thanks. Anyway, all right. So once you get your virtual machine running, you should see a virtual machine like this, just a Windows 2008 machine, and the desktop will probably turn black to punish you for not having a product key, but it runs. And when you start it, it may make you wait 15 seconds to bug you about not having a product key, but then it launches. So we're going to use various tools here, and there's a folder on the desktop, which is the Practical Malware Analysis Labs, and this is the binary collection. This has all the fake malware. So these are the programs we're going to run and analyze, and some of them do mildly irritating things to your machine, but none of them completely wreck your machine, and none of them spread. So in order to do malware analysis, the modern technique is there are 4 levels. You can do basic static analysis where you look at an executable and you try to figure out what it does without looking at the code and without running it. So this is the equivalent of going up to a Christmas tree and opening a package and trying to shake it and feel the outside and try to tell what's in there without even opening the package. It's very superficial, but it's very easy. For example, you could upload it to VirusTotal and see if somebody else has already analyzed it. That would be nice. Then you don't have to analyze it at all. Then the second one is the most fun and most exciting, basic dynamic analysis. The only problem is it's kind of insane. You run the malware deliberately in the machine and infect it. And then while you're doing that, you run a bunch of analysis tools on the same machine at the same time and try to see what they're telling you. Now, there are enormous, obvious disadvantages to this. You're going to harm a machine. You're going to infect it. It may participate in crime. It may join a botnet. The bad guys may notice that you're running it. And that might have consequences like, for the simplest one is it might notice it's running in a virtual machine and refuse to run correctly. The bad guys might even have put something in the malware that prevents your analysis tools from running correctly or causes them to give you the wrong answer. So this is quick and sloppy. And here I reach the most important thing to understand here. You are not doing a beautiful, precise scientific activity where you go through a clearly defined set of steps and you get always to the end. What you're doing is fighting criminals, and the criminals are intelligent and they're constantly changing their attacks. So you're much more like somebody in a fight that is grabbing one weapon, and when it doesn't work, you grab another weapon and you grab another, and you really don't know which ones are going to work because all the tools are kind of half-baked and incomplete, and all the malware is constantly evolving to fool your tools. So you just have to learn a lot of techniques and use scatter fire. So this static analysis, basic static analysis, is very superficial, but if it works, that's great. This dynamic analysis involves making some assumptions that are not always true, like the compromised operating system can be trusted to run analysis tools, but most of the time that's good enough. You just have to remember you can't really trust any of your tools too far. Then you got advanced static analysis, which is what I talked about in the original case. You're actually going to look at the assembly code and read it to figure out what it does. Now this, of course, is the closest thing to a perfect scientific approach that will really find out the answer. The problem is it's far too time consuming, so you try to avoid this as much as possible. And you try to use the other techniques to zero in on whatever small piece of code is most interesting and only bother to analyze that. And then advanced dynamic analysis is the last. The most difficult technique is the advanced static. The advanced dynamic analysis gets easier again. You run the code in a debugger. This is different from the basic dynamic analysis because instead of just infecting the machine with the malware and seeing what it does, you have the ability to stop the execution and modify it, to step through the code, and that will be helpful if your malware is a little bit advanced. For example, it has strings you need to see, like the URL of the command and control center, and it doesn't just store those strings in the usual way, it stores them in some encrypted way. With advanced dynamic analysis and buggers, you could run the malware until it decrypts the code and then stop it so you can see the decrypted value. This is quite handy. And then we'll talk about kernel hooks and rootkits of a simple kind. So if you do these challenges, you'll end up on a scoreboard. It appears here. Some people have been doing them in the last couple of days because this has been up for a while, and you see there's just a list of them. So you can see as you move ahead here. You can put any name you want. All right. So let me just demonstrate the first couple of these, and we'll see who wants to do it right away. This stuff will all remain up there for forever, for free. You can do this stuff later if you want. But anyway, let's take a look at basic static techniques. So you've got some malware in the folders there. The first one is Lambeau1.exe and Lambeau101.dil. You can set it up to virus total, and it'll, of course, be detected by some of the antivirus engines, but this is fake malware, and that's not really very interesting. So let's move on up to PEView. And this helps you see how Windows software works. So PEView is here. And if I open the exe Lambeau101, what you're seeing here is a portable executable file. All Windows executables, exes and dils, are all portable executable files. They have this format. They always start with MZ. They always have this message, this program cannot be running DOS mode. And then they have a long binary section. Now, one thing you could do is just scroll through all the binary in the file this way and view it. And that's not very easy to do, but that is the truth, of course. And you can also see the structure of it here. And take a look in the upper left, you'll see there's a text data, a .r data section, and a .data section. Portable executable files have these sections, and you can have as many as you want and any name as you want, but they always have text, R data, and data. A general rule for all Microsoft names is that they always are named the opposite of what they are. So the text data does not contain any readable text. It contains unreadable assembly language code. The text is actually in the R data or the data section. And here are those sections. This is the so-called text section, which as you can see is unreadable. It's assembly code. Here's the R data, which contains the name of routines that are being implemented. And here's the data section, which contains some stored strings like warning this will destroy your machine and so on. And notice another thing to get used to seeing is Windows API calls. If you have done Windows development, you will be used to this. If not, here's how it works. Microsoft does not authorize a user to touch the hardware. If you're writing a program like, say, Microsoft Word, and you want to print something on the printer, you are not allowed to. You cannot send any signal directly to the hardware. What you have to do is ask the kernel to please do that for you. And the kernel is written by Microsoft, and it offers you only certain functions available. So you have to make a request to the kernel API call saying, please send this to the printer, and it will then do it for you. And Microsoft has some naming conventions. So you see close handle, unmap, view of file, and so on. They always have these words rammed together with the first letter of each word capitalized, and they often have a capital A at the end, meaning ASCII, or a capital EX, or even 2 or 3 EXs, meaning these are extended versions of functions that existed before. And here's the name of a DIL file, kernel32.dil, and we'll be talking a lot more about these DILs and API calls as we go ahead. Now, for the moment, for this first thing, the main thing we're going to look at is the time date stamp, which you'll see in the image file header here, which is inside here, there. If you've seen any Kaspersky reports analyzing malware, you will have seen this. You see here the time date stamp is 2010 and something. You can tell if 2 or 3 files you find on a suspect system have exactly the same time date stamp. They were all compiled together as part of the same bundle, and that helps you associate them. And what Kaspersky likes to do is look at the time zone for this stuff and then do attribution based on this. So you find what time zone on Earth was that during normal working hours, and then you can decide whether it's the Russians or the Chinese or the Americans doing it. Like other attribution techniques, it's not foolproof at all, but it is commonly used for that purpose. All right, so that's PE view. That gives you some insight into the structure of your portable executable file. Let's try PEID, which does a similar thing, but as I mentioned before, we're going to use a lot of tools that more or less do the same thing, because you have to have a lot of tools to try, because they are all relatively unreliable when confronted with malware. So if I go here onto my desktop, Practical Malware Binary Collection, Chapter 1, and let's open the DIL, for example. Okay, the point of PEID is to tell you what language the file was written in. This one says Microsoft Visual C++. If you use a normal compiler and just compile files, it will put marks that this program can easily find, and you'll see what it's made of. If an attempt has been made to obscure the compiler, then you might get nothing here, or you might get indirect information, which we're going to see later. All right. And then there's BinText. If you've used the Linux utility strings, that's good, but it tends, I think it only picks up ASCII strings. BinText is a McAfee tool that does the same thing for Windows, and it's more powerful, doing both ASCII and Unicode. So you can open BinText, and then you can open a file. This is a very handy utility. It is not very smart, but it's very easy. All this thing does is it goes through any file you give it, and it looks for any string of printable characters longer than 4 or 5 characters, and just displays it in the order in which it finds them. So here's that message you see at the start of every file. This program cannot be run in DOS mode, and on it goes. Here you see some API calls: close handle, unmap view of file. We saw those earlier. Create file, find next file. And down here, we see C, Windows, System32, current E132.dil. So right now, we can already get a pretty good idea of what's going on with this file. And let me explain another important philosophy in malware analysis. When you're analyzing malware, you do not want to figure out everything about it. You don't have time for that. What you want is certain specific things. Usually what you want to know is, how do I detect it so I can tell which other machines are infected? What did it do so I can decide how to clean that up and whether I need to go through breach notification and all that jazz? And how can I scan and what are my indicators of compromise I can use to find it on my network? And there, or on your host. So there you're looking for files that are created, registry keys that are made, or network traffic it produces, such as beaconing back to the command and control center. So in this case, we can see almost all of these very easily right here in BinText. At the start, I see some Windows API calls, and from them, I can get some information about what it does, just by sort of guessing. I see a series of file manipulation API calls: create file mapping, create file, find next file, find first file, copy file. It looks like it's looking through folders on the system for a certain file and making some kind of a copy of a file if it finds it. So that gives me some clue what it does, suggesting that it's going to create a file, and that might be an indicator of compromise. Then if I go down, I see some low-level function calls, and now I see something that really looks valuable. I see kernel32.dil, which is a real Windows system call, a real Windows system file, and then I see kernel132.dil, which is very close to kernel32.dil, but off by one character. And that's what malware very often does, is make a file to try to masquerade as a legitimate system file to confuse people. So it's very likely that that file is produced by the malware, and if I find a system with that file on it, that's an indicator of compromise. And here's the whole path. See Windows System 32, kernel132.dil. So that's very good. That looks like a file-based indicator of compromise. I do not see any registry keys made here, so that's interesting. And I don't see any indication of network traffic. I don't see any IP addresses or API calls that say something like socket or internet or domain names at www.something.com. So that's my cursory analysis. I've learned quite a lot from this tool that's very easy to use, but remember, I don't really know that any of this is true. I haven't even verified that any of these strings are actually used in commands. They're just strings that appear in the file. So again, it's a relatively superficial analysis, but if the malware is not very smart and isn't trying to hide what it does, you can get quite a lot out of this analysis. All right, and the last one is DependencyWalker, which is the most difficult to interpret, but it does look in the most depth of the ones we're using in this section into the malware. So let's run that one. You can start all these tools by clicking Start and just typing a few letters. Here's DependencyWalker. And let me see which one I wanted to do here. Lambeau101.exe, okay. This one, all right. Now what DependencyWalker does, and here, let me see if I can make my font bigger, because I can zoom in here, but I'm rather afraid that the Zoom doesn't let the remote viewers see it that way. So let me try going down to this. Let's see if that'll work. And it looks like it didn't do any good. All right. I'm not sure I can do any better. I'm going to make one more try. Does that say how? No, that's size. Just font size. Okay, let me just try this. Let's try making it bigger. All right, I'm going to restart my machine to see if that makes things bigger, because we got plenty of time, and I'm concerned at how small this is, that it might not look any good on the video or the remote. In fact, I don't know how many people are viewing or whether they can feed in questions or not. If anybody has any questions, I would like to hear them. I guess that's up to Cheerio. Well, here comes the chat. That's good. Let's see. Looks good from here. Oh, good. Thank you for telling me. Okay, good. Glad to hear it. Well, I'm going to restart and see if I can make it a little bigger anyway, because I don't think it'll look good on the YouTube video. But anyway, then I'll carry on. All right. Is this allowed? It will be recorded. I certainly hope it's being recorded. And I think I saw on Twitter it's going to be recorded and put on YouTube, which is good. It's fine. Yeah, it will be recorded. Cheerio says it'll be recorded and put on YouTube, which is good. I'd like to put it on my webpage too, because I get a lot of people that want to watch these things later. All right, there we go. So I told you it would make you wait 15 seconds every time you restart. So it's doing that here. All right. Okay, good, good. I'm glad to see a bit of chat, so I know I'm reaching people. All right. Activate later. It starts, and I thought things might get bigger, but maybe not. Anyway, let's go back to DependencyWalker and open that file. All right, and I'm not convinced it got any bigger, but I'm not going to struggle with it anymore. All right, we'll carry on. So here's DependencyWalker. As you probably know, Microsoft uses dynamic linking. This is very dangerous and unsanitary, but it makes programs smaller and makes them load faster. And it's a decision Microsoft has made to make it easier to sell software. So SLNGR minus rearm, then reboot to get rid of the activation message. Oh, I didn't know that. Thanks for telling me. I knew that worked to extend a trial period. Anyway, so here's the exe file here does not contain all the code you need. It uses Microsoft libraries, and those are in these libraries, kernel32.dil and mscvrt.dil, msvcrt.dil. And if you click on one of these, you'll see the imports and the exports. The imports are the functions it actually uses. So we saw these before in the strings, things like copy file, find first file, and find next file. And now we can verify that not only do those strings appear, but they're actually used as imported functions. And these are the functions that are used in the libraries. So you can now see which libraries are used, and you can see which precise functions are used. And here is something called string comparison. So it strongly suggests that it's hunting through the file system, trying the next file and the next file, and then comparing the string, looking for a certain name, and then filling it in, and making a decision based on that name. And here's ntdil.dil, which is the kernel. Normally, programs do not call ntdil directly, but they call these other programs, which then call dil, like kernel32. All right. And let me check the chat, see if anything there I should do anything about. Rainbow cache on twist. How often is malware easily analyzed statistically? Well, I can't really say. I haven't analyzed enough real malware. I've just done the fake stuff in these classes. So I can't really say. I do know that in general, almost all hacking and crime has a large population of low-level attackers that use simple attacks, and the advanced stuff is more rare because it's more expensive. Anyway, let me see what particular things I wanted to find in this one. All right, so anyway, here you can see some of the calls like create, process, and sleep. And again, you can guess what it does by looking at the particular functions it calls. The DIL file, labo1.dil, does appear to connect to the network. These are standard Berkeley API sockets, connect, accept, and bind. So here's how you get points in this thing. You put in your name and answer these questions. If you analyze this sample using some of those tools, you can find the name of the file it downloads and put it in here. And here you can find a function name that it pulls in from this DIL using these tools. So when you do those things, you'll end up on the scoreboard, like these folks here. And that is the first two projects. So see some people are up there. I know Em was doing it earlier today. I'm not sure if anybody's doing it right now in the live stream. Anyway, so that is the first one, basic static techniques. And the unpacking is the only remaining skill in this section. So let's take a look at labo102.exe with BinText. So BinText is here. And if I go to chapter 2, oh no, labo102, this one, all right, and go. Okay, so here are the strings, and there's a couple things to notice here. One is there are very few of them. There were more pages of strings before, and all I see here is kernel32 win inet, implying some kind of networking, get proc address, and almost nothing else. This is a very small selection of strings with very little information in them, and the reason is this is a packed malware. Packed malware is like a self-extracting zip file. All the strings are scrambled, and the only thing I'm seeing here is the unpacker. And when you run it, it automatically unpacks itself. So to find out what's going on here, I can use PEID. If I take PEID and run it on labo102, which is desktop, here, labo102, okay. I see no name of the program that compiled it. Nothing found, nothing like C++ or Microsoft Visual Basic or anything. But up here, the name of the section is UPX1. Here's the sections, UPX0, UPX1, and UPX2. This is a common open source packer called UPX, and it renames the sections to have this name. So I know what packer is used just by recognizing that. And since it's open source, I can get the packer and open up the malware. Okay, here's saying, how will the CCSF be active? I'll just leave it up. It's been up there for more than a year now. I'll just leave it up and you can keep using it. All that happens is before events like this, I archive the scores, and you'll find the old archive scores at the bottom. That's a good question. Oh, by the way, this stuff is all available for anyone to use anytime. You'll find on my homepage a use policy that has made it all open source for anybody to use any way you like. Important thing I like to mention so people know. All right, so let's go back to PE View, and so you can, well, if you do open it in PE View, I don't think I'll bother because you already found the same information in PEID. You'll see that the sections are all named UPX 0, 1, and 2. So you can open it with the UPX Unpacker. And that's here, it's a command line unpacker. All right, let's see, I've got another chat here, if I can bring it up. Okay, good, people are happy. Oh, please mute yourself, people that are not on mute. Oh yeah, if you can mute the people, that would be good. You have to do that as more people add. It's not too bad, but we do hear a few clicks and stuff. Anyway, so UPX is a command line unpacker, and you can just do UPX -D on this file to unpack it. Put the output in the unpacked file, and when you do, you'll see the original file was only 3 kilobytes. The unpacked file is 16 kilobytes, much bigger. And when you run the strings on that, you'll see the strings on the unpacked file. So, and you can get in the scoreboard by doing that. So let me see if I've already got the unpacked file in here. If not, I'll do that. Let me go to desktop and practical malware analysis. And I think it's binary files, binary collection. And then let's do dir again. Okay, chapter 1 should be someplace down here. There we are. And there are the files. Okay, I don't have the unpacked, so let me just unpack it, which is this command here. px -d. All right. And hopefully my copy and paste is going to work. Hey, there we go. All right. So that unpacked it, made it go from 3,000 bytes up to 16,000 bytes. So now I have a file called Lambeau 102 unpacked. And let's just take a look at the strings to see what we can see. So that's Lambeau 102 unpacked. And go. Okay. And now, still don't see too many strings, but I do see something called system time to file time and create mutexes. Mutexes are important for us. Mutexes are handles created in the file system that are shared between processes. So if you have one process using a file and you want another process to use the same file and it has to make sure the first process is let go, then you use a mutex to record that. And malware often creates mutexes just to mark that machine as infected. Typically, when malware is started, the first thing it does is check to see if this machine is already infected. And if it is, don't bother to try to infect it again. And a common mark is a mutex. So this is likely to lead us to an indicator of compromise when you understand that mutex. Let's see what else we have here. I have a URL, http www.malwareanalysisbook.com. That's a good idea. And here I have some high-level networking calls, Internet Open URLA and Internet Open A. So this malware might be connecting to a website and downloading more files, or that might be the command and control center that it sends periodic beacons to indicate that your machine is owned. Here is more about the mutex, more about the internet, and another repetition of looks like the same URL. So that's pretty promising, and certainly a lot better than the strings that I saw before unpacking the file. Let me go back to my instructions and see what I'm looking for here. Yeah, and now if you run PEID on the unpacked file, it'll tell you it's Microsoft Visual C++. It's no longer hiding it. And if you look in DependencyWalker, you'll see Internet Open URL and Internet Open A, as we saw them in the strings, showing that it is opening a URL. So we found a URL used by the malware, and that's very helpful because then we can just scan our network to find the infected machines. Network-based indicators of compromise are very handy if you have a large company network. So there's a couple more challenges here, which are very short. They're just ways you demonstrate mastery of these. There's a general philosophy in all this. There's a project you do that tells you exactly what to use and has screenshots and shows you step by step. And then after that, there's ones without instructions, so you get to practice using the tools. So here you have to find the packer used by this for this one, and you'll find a packer name, which is 3 letters. Not going to bother unpacking it, but you have to find the name of the packer. And this one here, you have to find the date stamp showing you when this sample was compiled. So those are challenges. Several people have already done them. All right. So now let's talk about dynamic analysis. Good. And I see we're half an hour in. I think we're doing just fine on time. So here's basic dynamic analysis. Now, usually before you do dynamic analysis, you do static analysis to decide what needs to be done. So PE view is here. You can examine strings, and you will see a registry location, software classes, and then a URL and the name of something called video driver. So those give you some idea. It does something with the network and it does something with the registry. So now we can run dynamic analysis. Now, the way dynamic analysis works is you turn on some monitoring tools and run them so they are monitoring the system. Then you launch the malware, and then you see what it did. So we're going to use Process Explorer, Wireshark, and Process Monitor, because the static analysis has given us a clue. There is some kind of network traffic because we saw URLs, so we want Wireshark. There are registry keys being created, so we want Process Monitor, and we're going to use Process Explorer too, just to see what's happening while the malware runs. So let me launch those tools. Let's get rid of this one. Process Explorer is here. Process Explorer is just a souped up version of Task Manager. It shows you a live view of all the systems running, all the processes running on the machine. For example, let me bring up Task Manager to compare it. Anybody that does Windows desktop support is used to Task Manager. This is the first stop to see, why is a machine running slow? Do I need more RAM? Has some process hung? So it shows you the applications you've launched, which in my case are just Process Explorer. I'm not running anything else. And then the process the system is launched, which is 43 processes on this older version of Windows. And you see things like SVC host and WinLogon and LSASS and so on. And you notice if you sort by image name, there are a whole bunch of SVC host processes running on a normal clean Windows system. And Process Monitor Task Manager rather, doesn't really tell you much about them. It's not even clear why they're running. All you can tell is there's a bunch of them and they're running under different identities. So if you wanted to understand these, this tool is not very helpful. And Process Explorer is much better. Here, it colors them. So the services run in pink, and these SVC hosts show up here. And if you hover over one, it tells you what it's doing. So this service host is running function discovery, network list service, Windows Time, Workstation, which is a file sharing service. This SVC host is running desktop window manager, session manager, and network connections, and so on. A lot of Windows runs as services, and each SVC host executable is hosting a group of services. So it's easier to see what they're doing. Anyway, this shows you a ordered structure of everything in the machine. The idle process is just the leftover CPU that's not in use, which is nearly 100% on my system because I'm not doing much of anything. Then comes the system, which launches the machine. Then when Windows starts with Win init, it then calls WinLogon, which is coming down here. It launches all these services, which start Windows, and all these services run before I've logged in. Then, after all these things have launched, it launches WinLogon. That is the process that displays the login menu where you can put in a username and password. Then, after I log in, I launch Explorer.exe. Explorer.exe is the parent of everything the user does. It draws the desktop and the start button. So everything you do by clicking the start button or icons on the desktop or launching something from a command prompt is a child of Explorer.exe. And Process Explorer shows that as indentation. So Explorer.exe is indented to this level, and everything I launch after it is indented more. So here's VMware tools, Here's something called VMX32 to 64, which is going to turn out later to be created by one of these fake malwares I've run. Here's the Java updater, and here's Process Explorer itself. So that shows me what's running right now. Now, let me just check. I think I have to kill that VMX32. Yep, okay. So here, my virtual machine already has this malware running, so I need to go through this troubleshooting process to get rid of it. So I'm going to have to kill that process and then delete this file, because this malware creates a file in the system and it won't reinfect the same system again. So let me do this before I get in trouble. Delete, kill this process. Okay, and then delete this file. All right, and now my machine should be clean, ready to be infected. So that's Process Explorer. Now let's run Wireshark. I've got an older version of Wireshark installed on this machine, but it's good enough for our purposes. Here's the connection that has into network traffic, so I'll just double click on that and give it a password. I think I changed my password. All right, so now it's sniffing my network traffic, and there's not too much going on, but there is some network traffic going by. All right, and then I want to run Process Monitor. Process Monitor is another sysinternals tool, as is Process Explorer, and Process Monitor is monitoring Microsoft Windows event log. And Microsoft Windows event log is very noisy. 100,000 events so far, 110,000, it's counting up very fast. And right now I have pre-configured it to ignore all the things that are happening before you launch the malware. If you want to adjust that, you can go into filter, and here you can tell it what to include and exclude. And what I've done is just exclude things by process name for everything that was running. Process Explorer, System, and so on. This is a very sloppy activity. Anything with these names is ignored. So if the malware used exactly the same process name as some innocent process, I wouldn't detect it. Remember, we're not looking for perfection here. We're looking for a quick, dirty analysis, hoping that the malware is relatively stupid. If it is, then I don't have to be fancy. I can just detect it with a simple scanning process like this. So I exclude all the harmless processes, and now I run Lambeau301.exe. Let's move this stuff aside and go here and run Lambeau301.exe. Okay, I'm going to shove this to the side and make sure I have Process Monitor, Process Explorer, in the front so I can see what happens. So down here is my user land. Now I have Wireshark running, and I have Process Explorer and Process Monitor, all children of Explorer. And when I launch this Lambeau301, then I have that. It appears in green, and then it stops. And then I expected to see a VMX tool. We'll see what happens here. All right, so I launch it. Now I should be able to, in Process Explorer, go to View, Lower Pane View, Handles, and see the mutant. Let me see what this message says. Thanks for someone for the Zoom. Okay, fair enough. All right. All right. So if I go to Lambeau301, then I can view Lower Pane View, show Lower Pane, and these show the DIL files that it uses, which is not what I want. I want to see handles, and that's here, handles. Okay, handles are named objects created by this, and I can see a mutant named WinVMX32. So this has created a mutant, as I described before, to mark this machine as infected. So if another copy of it tries to infect the machine, it won't work. And, all right, that created the mutant. Now I want to view the DILs. If I view the DILs, I'll see some TCP/IP DILs, indicating it's going to do some network traffic. Now I should be able to view events in Process Explorer, Process Monitor here. And there they are, showing up very nicely. So these are two files that passed my test. It wrote a file, C Windows System 32 VMX 32-64, and it set a registry value, which is here in the run key called video driver. This is very common. It's created a file, VMX 32-64, which is an executable that will relaunch the malware. And this is the persistence mechanism. If malware takes over a machine and places it under remote control, you will lose control when the user restarts that machine. So to prevent that, you have to make it automatically start every time the machine restarts. And there are, unfortunately, 30 or 40 ways to do this in Windows. These things are called auto start extensibility points. And the best tool to find them is a sysinternals tool called autoruns. However, the most simple, obvious way to do it is to use a run key. Well, perhaps the startup folder is even simpler, but anyway, there are a few run keys. So any link put in the registry in the run keys will automatically run on restart. This one puts itself in a key in a video driver container to make it look like a video driver of some kind and gives it this name VMX 32-64 to try to look innocent. So these are more useful indicators of compromise. And the only remaining thing is I think I'm going to see beacons in here. Yeah. And by the way, we can see the event properties showing that this run key does in fact point to that file. So we double click the event here. Okay, this shows me the file, C Windows System 32, VMX 32-64. And if I look at the run key, you can see here, it does have this data, C Windows System 32, VMX 32-64. So that run, these two are connected. It's not just that they happened at the same time, they are connected. It created this file and it created a registry key pointing to that file. So from now on, every time you restart this machine, it will restart that malware. And let's look at the beacons in Wireshark. Here's some traffic going by. To detect the beacons, they happen to contain the word malware, so that's one way to find them. Frame contains malware. And you'll see a series of repeating DNS requests. Now, you could use any kind of network traffic in malware to phone home. Typically, when a machine is controlled, it has to send regular signals back home because the bot master has a control panel on a command and control server, and they're probably controlling thousands or millions of bots. So they've got a nice GUI on this thing, and it says you have 1,000 bots in this country and 10,000 bots in that country, and you can now issue them orders. So they're all constantly beaconing back to inform the control center of their status. In order for to make that beacon get out of the network and not set off any alarms, it hides masquerading as normal traffic. So it often pretends to be an HTTP request or a DNS request. And in this case, it looks like it's using DNS. Or actually, it's using HTTP, but it's doing a DNS resolution first. So you'll see it does a query to find practicalmalwareanalysis.com at time 135 seconds, and then 30 seconds later it does it again, and 30 seconds later it does it again. So it keeps on resolving this domain through my DNS. So this appears to be a DNS-based bot, and if I want to see the actual traffic that follows this, I'm going to have to find the DNS packet, like this packet 70, and then clear the filter to see the traffic after packet 70. So 70 did the DNS query that found the names. Packet 71 found, got a response telling it that that was at a certain address, and then it did a TCP handshake, SYN-ACK to connect to the address, and then it sent some data to that address. So I could analyze these packets one by one, but analyzing packets one by one in Wireshark is for losers. The cool thing is use Wireshark's more advanced features, like you right-click on one of the packets in this TCP stream and follow TCP stream. And now you'll see a nice layout of the layer 7 data with no addresses in it. This is very handy, and I highly recommend Laura Chappell's book, Wireshark 101, and the Wireshark certification. I did those things because it's very much worth learning how to use Wireshark. And it has a lot of features that make it a lot easier. And of course, this data doesn't mean anything. It's just random data because this is fake malware. If it was real malware, this data would contain some information about the machine, although it might be encrypted and look random. Anyway, those are the beacons sending regular traffic back to the command and control center every 30 seconds. And okay, and if you want to prove your points, you can download my saved file and analyze it and find a certain series of strings to show that you're able to do that stuff in Wireshark. And that's number 5. Close some of my other tabs here. And let's look at the keylogger. This is a fun one. I added this fairly recently because it was a lot of fun. So you've got to write a process explorer at the same time as Explorer. And then I'm going to launch Lambeau 303. So let me set this up. I don't need Wireshark anymore. And I don't need Process Monitor anymore. But I want to run Lambeau 303. Okay, good. So here we are. Let me get rid of the lower pane view because I don't need that. All right. And shove this to the side. Okay. All right, I guess that's as far as it's going, it'll do. So here is userland. Down here, Explorer and its children. And if I run Lambeau 303, watch what happens in userland here. It's going to be fairly quick, but it's not very subtle. So this should work. Lambeau 303, okay, when I run this, Lambeau 303 itself launches, it's green. Then Lambeau 303 terminates, but it created an SVC host child, and the child continues even when the parent has terminated. Now, this is really suspicious and screwy. Normally, if a program launches a subprogram, when the main program dies, the subprogram will die, and svc host.exe does not belong in userland. svc host.exe belongs up here in the system processes that launch before you log in. So if this is malware, again, lying to me and trying to look normal. And if you use a sloppy tool like Task Manager, it'll be not as obvious as it is here that something's wrong with this SVC host, but that SVC host is doing something improper. And in fact, it's a keylogger. And you may notice a file just appeared here called practical malware analysis.log, I think, or something like that. Let's get this name bigger. And that is a keylogger. And you can prove it by just typing in some stuff. If I open Notepad and I type in hello from San Francisco, all spelled badly, then that should all end up in that log. So if I open this file, open with Notepad is fine. You see, there it is, hello from San Francisco. So this is logging all my key presses and putting it in that file. And that's what a keylogger looks like here. Now, the keylogger is interesting. It uses a powerful technique called process replacement, which I found very useful. So if you go to the running keylogger process, svchost.exe here, and go to its properties in Process Explorer, you'll see Process Explorer properties are really informative. And if you look at strings, you can see the strings in the file right here. Let me make my window a little bigger. All right. Now let's check. I see a chat message going by from Twitch. Can you bypass 403? Well, I don't know. It looks like that's for somebody else. All right. Anyway, so here I have these strings in the image, and here's the strings in memory. So this is the SVC host file on disk, and it's just got a lot of API calls. But if I go into memory, I see a completely different set of strings. Now, this is not right. When you launch a process, there's an exe file on the hard drive, and when you double-click it, it copies that file literally into memory and runs it in memory. That's the normal situation. This is the malware technique called process replacement, where you take a running process and then you suspend it, change the contents, and then rerun it. It's a way for malware to get itself loaded into memory without ever coming from the disk file, to avoid antivirus, and to gain the privileges of another process. So that's what's happened here. All right, and you can test the keylogger as I did. You can see it working, and you can kill the keylogger process. And you'll find another file I made here, which is also a keylogger, and you have to find the file containing the captured keystrokes. So if you do, then you get points for that. All right. And there's a challenge here to find the beacons from a file. These are all slightly modified files. Here's a program called beacon.exe, and when you run it, it will go to a domain name, a command and control center. So you have to find that and put it here to get your points, to record your success. All right. Let me just see if anybody's doing this live. I think it looks like people are planning to just watch it later, but I'm a little interested to see the scoreboard. Normally I'm in the room with people, and I'm not sure I see any more people doing it. Yeah, here's a second name made of number. Okay, some people are doing it good. 4K Bomb is doing it. Anyway, when I do this face-to-face, I usually stop and pause and wander through the audience and help people and have students doing that and such. But for this online event, that's not very practical, so we'll just carry on. All right, so then let's talk about advanced static analysis. So we've now done the basic analysis without running the software or looking at the code, and then the basic dynamic analysis where we do not look at the code, we just run it to see what it does. So these are both quite easy. This is the most difficult part of the class, the one that scares people away, and that's assembly language. Assembly language, like math, is something people tend to have a phobia about, but it's really not that hard. The fundamental thing to understand about malware analysis is you are constantly confronted with way too much baffling complexity, and you have to not let that scare you away. You just have to figure out what you can about it and keep moving. Don't get bogged down in complicated details, because not only are the details very complicated and it might take you a long time to learn it, but also a lot of the details might be deceptive lies from the bad guy. So it's really not wise to let anything bog you down. This is my weakness in capture the flag competitions. I frequently start a difficult problem and go in the wrong direction and spend a long time banging my head against difficult problems in the wrong direction without realizing I just need to try another approach. And malware analysis strongly rewards this. So Jasmine, if you do not have any experience with assembly code, it's good to learn a little bit of assembly code. Even if you don't know much, knowing a little assembly code will make you a lot stronger. You can run Jasmine in any machine that runs Java, and it's already installed in this machine here. Jasmine is not specifically a malware analysis tool. It is a simulator just to make it easier for you to learn assembly code. So let me launch it here, and I'll just show you. I really like this product. I think it was made by German bankers or something. Okay, and all right, what this does is it simulates an x86 processor. So here you have the registers, and this is something you'll see over and over again as you get into binary analysis and reverse engineering. This is what's really going on in the hardware. You have a series of registers. Back when I started on the old 6502, there was one register named A, the accumulator, which dates all the way from mechanical adding machines. Now there's 4 of them, A, B, C, and D, and they've extended once to go from 8 to 16 bits and extended again to go from 16 to 32 bits. So it's EAX and EBX. Then the stack goes from ESP to EBP, and the EIP is the instruction pointer that tells the processor which code to run. Here's RAM. Memory is here, and it goes down to the bottom here. The top is normal RAM used by processes, and the end is the stack. So let's play a little few commands here. You just put code right here. And all right, so I can do move EAX1 and move EBX2 and push EAX and push EBX. All right, and I'd change my properties if I could. All right, I think I'll let it go. All right, so it shows you each command down here, and the green highlights the current instruction. You can step through the instructions. I think with this one, there. Move EAX1. That puts a 1 in EAX sitting here. Take a look at EBX. That puts a 2 in EBX. Push EAX puts EAX on the stack. If you scroll down to the bottom, it put that one here at the end of the stack, which is FFC. In hex, there's only a small amount of stack on this machine, and there it pushes a 2 onto the stack. Now I can pop the contents of the stack and put that in ECX, and I can add EAX and EBX. Let's see what that does. When I pop, that'll take the toppest thing on the stack called 2 and put it in ECX. And when I add EAX to EBX, I used to have 1 and 2. Now I have 3 and 2 because it took EBX and put it into EAX. This is the Intel syntax where the destination comes first and then the source. Anyway, those are simple commands, and there's a few others to make loops and such. And you can just copy and paste these into Notepad and write assembly code and run it here. It's a simple simulator, and it's a very nice way to understand how assembly works. So here's some code. That's how the stack works. And we've already done enough of that. Here's something that will reverse a sequence. Let me try this one. And let me just check this chat message to see if it's something for me. Okay, nothing else. Okay, good. All right. So this one, if I copy this and go here, I can just delete that and paste in this code. Now I can reset the machine back to 0 here. Should I reset it? It didn't seem to. All right. That's disturbing. Run and reset. All right. And maybe I'll just close the program and relaunch it. I seem to be somehow stuck. That should have reloaded it. Let me see what the pop-up says. Please reset the memory and all registers. Stop the program. Stop. Okay, stop and reload. Now I'm back to clean. All right. So now I can step forward. I'm going to put 1, 2, 3, 4 in the 4 registers, which is here. And there they go, 1, 2, 3, 4. Now I'm going to push them onto the stack. So it's push, push, and you see them going on here. By the way, notice this is real important. It moves 32 bits at a time. So when I push 1, it does not create a byte containing 1. It creates a 32-bit word containing 1 and 3 bytes of 0 for the high order bytes. That turns out to be real important when you write shellcode later, because your shellcode made in this fashion is all full of zeros and they terminate strings, which is an annoyance. Anyway, I push them on the stack. Now I pop EABX, EAX, EBX, ECX, and EDX. And when I do that, they're going to come back out of order. So now it went from 1, 2, 3, 4 to 4, 3, 2, 1. That shows the last in, first out nature of the stack. And the stack is designed specifically to handle the memory problem of having subroutines call more subroutines and more subroutines. And then when you emerge from subroutines, you have to recover those memory segments in reverse order. That's why the stack works that way. All right, so that's a very good tool to write some simple assembly code. And there's a challenge I wrote here where it does what malware does. If you download this file, there's a series of instructions. And if you run these instructions the same way, I'll load it here. Whoa, paste it in, there we go. I'm gonna stop, reset. And I said reset. Yeah. Okay, now it's gonna push a bunch of things on the stack, long lines. These are 32-bit words, so there they go, long things with 8s in them going on the stack. Then it's going to move something here and pop and do XOR, and that's going to create readable text somewhere. This is a very common arrangement. It loads some encrypted stuff, it decrypts it and puts it somewhere, and then it erases it. So there's one period of time in the middle here when you can read a message, and then it will be gone again. And I think in this case, you're going to have to find the message, which is just going to be spelling out ASCII numbers. There is actually here's some ASCII code appearing, 69 and 80. Those are ASCII codes. There is, in fact, a console in some versions of Jasmine, but I don't have it working on this one. So the closest you're going to get to getting something readable is just seeing ASCII text, I think. Let me go back to my instructions for this one, see which version of this one I gave you. Yeah, it spells out a secret message in RAM. So you will have to read the ASCII text, but you will find a secret message being spelled out there. This is something that really happens with malware a lot. It has something important like a password or a string, and it just creates it at one point in it, uses it, and then deletes it again. So unless you can run the code halfway through and stop, you'll have difficulty finding it. All right, then we should talk about IDA. This is the most difficult program I'm going to show you, one I'd seen before and decided it was horrible, and you really need a teacher and a book or something to give you an introduction to IDA, because more than any other tool here, IDA is way too complicated. But you don't have to worry about that. Like I say, the secret here is to think like a small child. You give a small child a book, they can't read, they will just look at the pictures. They don't have any feeling of being ashamed that they should know more. They just look to see what they can get. And that's what you have to do. Because IDA is going to present you with way too much information, and you just have to not worry about it and get what you can. So you launch IDA, which has a bunch of versions, but we're going to use, I think, the older free version here. There are 2 free versions. It has a splash page. Now you have to choose a file to work on, and the file we're going to work on is crackme121-1, which I wrote imitating a series of challenges in that European HoneyNet Alliance project. So I double-click that one to load it. Now it's going to ask me, how do I interpret this file? I'm just going to accept all the default values and say OK, and here I'm going to say yes, right, about debugging. Just accept the default for everything. But it is important to understand what IDA is doing here. IDA is actually guessing to figure out how this code runs. It can make mistakes, and malware can be written in ways to fool it. But in a simple case, it can analyze it. Now, IDA is not done yet. It's analyzing stuff. It takes a few seconds. I think it's done now, but notice this colored bar up here. While IDA is still analyzing malware, this bar will be changing, and you can't use it until it's done loading, which can take a few minutes. That was one thing that confused me at first. Now, here's another thing. I have 6 or 8 toolbars full of icons. I've got tab after tab and windows everywhere. I just want to stop and give up. So you have to simplify this display a little. The first thing I'm going to do is maximize this view here. So all those little windows all turn into tabs. And now here's another very annoying thing about IDA. The whole point of IDA is it should show me the code that runs that program. But it shows me this garbage, attribute thunk public start and nothing else. For some reason, what it does is it shows me the loader, which Windows is going to use to load the program. It doesn't show me the interesting part of the program, which will contain passwords and indicators of compromise. It shows me some boring system routine that loads the program. So to find something good, the easiest way is to go to the Strings tab. Now here is something familiar. These are strings just like we saw before. By the way, these are not strings like you saw in BinText. This is not just series of bytes that are readable. These are actual strings used by the code, because IDA is much smarter. But notice what you see here. Fail, you found the password, top secret. Okay, and let me start, which I should have done earlier, but let me do it now, by showing you what this stuff does. Here's the challenge. This is a sort of common hacking game. In the C IDA folder, there are these things called crackme, and if you run crackme1, it tells you usage, crackme1 password. So you put in a password, a pass, and it says fail. And whatever you put in, you get fail. There is apparently some correct password you can use, but you don't know it. And this challenge is just to find the right password and get the win message. So that's what we're trying to do here. So that's what's going on here. Fail, you found the password, and top secret is sitting here, and then other technical things. So this area, like you found the password, is the message I want to see. So I'm going to double click that, and IDA will now show me where that is stored. This is an R data section. Remember earlier, we talked about the portable executable format. The text section contains executable code, and the other data stores things like strings. This is where the string is stored that says you found the password. Now, I don't really care about reading this string. I care about where is the code that used this string. So that is here in the data xref. If you click on this section here, it turns yellow, and there a box pops up showing the code. And if you double click on it, IDA now shows me what, in my opinion, it should have showed me right from the start. It shows me the routines that actually use that string. And here's the routine that prints out, you found the password. Let me check the comments here. Okay, Twitch is saying your laptop battery is low. Not mine. Oh, mine. Oh, by George, you're right. Thank you for telling me. I thought I had plugged it in, but I haven't. Okay, now I plugged it in again. Good. Anyway, so here we have the code that says you found the password. So now if I get the junk off my screen to get as much usable screen space as possible here. There we go. Whoops. Okay. And go back here, we can now see this is the code that the developer actually wrote, the place I probably want to look at. Here's some kind of launch routine, which does some comparison with the number 2. And then depending on the result of that, it goes to one or two places. It either goes here and prints the usage message, or it goes over here and then decides something about the password. So that's the original launch routine. This is the line that says how many arguments were there in the command line. If there were not 2 arguments, then you have to go print the usage message because it was launched incorrectly. There should be exactly 2 parts to the command line, name of the program and the password. So if you do give it a password, it goes here. It now refers to a fixed variable called top secret and compares something to that. And then it makes a decision and prints either you found the password or fail. So, as you would expect, it's pretty obvious. Top secret is apparently a password, the stored value top secret. So from reading the code, I was able to figure that out, even without bothering to really understand where all the calls and adds and JNZs are going, just by doing what a little kid would do. I look for the part I can read, like congratulations and you found the password, and the general structure of the arrows. It's enough to get an idea of what's going on here. And this is a more accurate procedure than just using strings, because I really am following the logic of the code as well as IDA can figure it out. So now I should be able to win the game. It's apparently top secret. And I find the password. So the challenge is to crack these other ones the same way, and each one is, of course, a little bit harder. But this is a simple beginner's exercise to get you used to using IDA Pro. All right. Now, those are crack me's, and another one you can do is open this one here, labo501.dil from the malware. We're going to find the command and control center for this labo501.dil. And what I just showed you was challenge 11. I didn't do them in order, but now I'll go back and do challenge 10. And realistically, it probably would have made more sense to make challenge 11 come first because it's simpler. Challenge 10 uses something closer to real malware, which is a little more complicated. So let's do that. Labo501.dil. File, open, okay. By the way, whenever you close a file in IDA, it's going to offer to save the database. Normally, you might spend hours or days analyzing a file and you'd be filling it with comments and marks. I'm going to not save the database because I'm not using IDA in such a sophisticated way. So I'm going to go here. It's labo501.dil. There it is. Okay, again, I'll just take the default values and let IDA analyze it and maximize the command window, IDA view A window, to see what we've got here. And it took that long to analyze and didn't really show me this graph view until then. And so now I'm in here. When it's done, you'll see this file. Okay, now I would like to maximize the window, do all this garbage. Okay, now I'd like to see the opcodes for this one. I'm not really sure that's necessary, but it's a good practice. Options, general. If you look at this line of assembly code here, IDA has given you a block of code, and here it just has move instruction, but it doesn't even have addresses, and it doesn't even have the raw hexadecimal value of the code there. So that is simplifying things a little too much for most analysis. I'd like to have more information here. So I'm going to have to give it 6 bytes of opcode, and I think, yeah, it's line prefixes is the other thing. this will give me a more informative view. Now I have the actual address, and this is the actual hexadecimal value of the instruction. So it makes the Windows thing a little wider, but it gives me more information. Notice I have many repeats of the same address here, which doesn't make any sense. This is not real assembly code. This is a comment generated by IDA to try to make it easier for me to understand, hopefully. This is dill main, which is loading a library. All right, now that makes it more visible. Now I can go to text mode. If I use, this is the mode that puts the code in little boxes and connects them by arrows to try to make it easier. If I want, I can press the space bar and just see it in this other mode where you just see lines of code. And this is the stuff I knew about from decades ago that I thought was so baffling I really didn't want to go here and try to analyze this stuff. But of course, IDA can present you with that view if you want it. So now there's a Windows API call called getHostByName that does a DNS resolution. So if I'm going to connect to Command and Control Center, I'll be using this thing. So I would like to find the Command and Control Center's name by finding getHostByName. So we can go to Imports and go to getHostByName. So Imports is right here. And here they are. We can sort them by name, and then we can go to the G's and look for getHostByName. One irritation here is the sort is very primitive. The sort sorts by ASCII number. So the capital G's are here, but getHostByName uses a lowercase g, so it's all the way past the capital Z's. You have another alphabetical list, and there's getHostByName. So it does import from the Windows DIL, WS232, getHostByName, and use it. Now I want to double click it, and then Control X to get all values. It's double click, which gets me to a call for it. And then I think Control X shows me all the cross references to it, not this one. So I can now see that there are, I think, 9 places in the code where it does a call to getHostByName. So the one of particular interest here is the third one from the bottom. And I double click that one. And that gets me to this call, which gets a host by name. And okay, and I can find the offsite. I'm going to find the command and control center here. So let me go back to graph mode. Okay, so here is another thing to get used to. This is how function calls look in assembly code. You don't just call a function, you have to send it arguments. So if I'm going to make a DNS resolution, I have to pass in the domain name. And the way it always works is you always see push call, or several pushes and then a call. Possibly moves instead of pushes, but it's usually a push because arguments move on the stack. You put a bunch of code pointers on the stack to your arguments, or just values of arguments, and then you call a function. So it puts this value EAX on the stack, and the EAX is a calculated value. It takes an offset value, which is a memory address. It then moves it and pushes it on the stack, and then calls getHostByName. If I hover over things, IDA tries to help me by popping up information. So here it tells me the name is the one parameter for getHostByName, char star, so it expects a pointer. So this must be the pointer. And if I go up here and point to that offset, it's going to tell me pix.practical malware analysis. It's showing me part of the domain name right there. And I can double click that, and it will take me to the stored data, which is down here. And there's a way to see it in an even better way, which is the Hex View A tab. This will show me just a direct dump of it. Let me go back to here. I want, there, this thing here is 100.190.40, or, oh, the data xref here, okay. Let me go to this data xref. That's the one, okay. Let's try the HexViewA 100.109.40. There it starts. This is the pointer, which is 10.01.91.94, which is just off my screen. This is a pointer to the value. And if you scroll down to it, 91, 94, it's here starting in blue. It has brackets. This is RDO, then pics.practicalmalwareanalysis.com. So that is the URL of the command and control center. The bracket part is removed, and then it uses pics.practicalmalwareanalysis.com. So that's an example of how you could find something useful in IDA, although obviously there'd be quite a lot of time analyzing things to zero in on something this specifically. But it gives you some very shallow flavor of what sort of thing you can accomplish inside IDA. And here's another one. Let's find the code that launches command lines from the criminal. So if we go to strings in IDA, you'll see the strings that are actually used. Up here we have shell, bit, get module, and copy file and all that jazz. Let me sort it and find the thing that launches command, because the special characters will sort together. And I'm looking for backslash, which is there. That's dot backslash. And someplace around here I'll find backslash. There's letters. And here's the capital Z coming up. Okay, then there's my backslash. This is the one I was looking for. Backslash cmd.exe/c. This is the command line to execute a code. And if I run that, I'll get that stored string. And down here, I see more useful strings that give me a pretty good clue what's going on here. Hi, master, are you enjoying today? Uptime, the magic number for this remote shell session. These are messages sent back to the bot master indicating the status of their bot. And if I double click it, click the IDA View A tab, and hit Control X, which we did before, IDA View A, Control X. I now see how many cross-references there are, and there's only one at this location. So that string is only used once. So if I double click it here, I will see the code that actually uses it. And notice that it either uses CMD or command, and it bases that on a decision made up here, which called a system directory. And so what's going on, if you scroll back here, we can find some of those other strings we saw earlier. There's a carriage return line feed. Hi, master. So this is the interactive component of the malware that the master uses to send in commands. So it tells the master the welcome message, then it gets some data from the master saying, execute this command. Then it goes down here and it checks the system. It calls some Windows API call to look for a directory, which is probably looking to see if it has a C Windows System directory or a C Windows System 32 directory or something like that, because it makes the decision to send either the 32-bit command line, CMD, or the 16-bit command line, command.exe.c. So that's what's going on here. You can now more confidently say what's going on here. This is a botnet command and control. This is a bot infector, and in particular, this part of the bot is the one that executes arbitrary command line commands. All right. So that's what I wanted to show you there, give you some introduction to how IDA works. And then I have advanced dynamic analysis. Got about 40 minutes left. I think we're in good shape. This is the hardest part, what we just did, that assembly code. Advanced dynamic analysis is a lot more fun. OllyDbg is a hacker's favorite friend. This is used to cheat on Windows games. It's been around forever. You can modify code. So we're going to modify PuTTY. Let me get rid of IDA, and we're going to use Olly instead. Don't save the database. Let's start looking at PuTTY. If I go into my documents folder, I've got a somewhat older version of putty.exe here. I'm going to copy and paste it just so I don't mess up my original. And oops, I wanted F2, but I hit F1. Okay, I'm going to call this PuTTY2. Okay, oops, I don't want to change that. I don't want to lose the exe. Let me try that again. F2. Okay, there we are. PuTTY2. Okay, what PuTTY does is just an SSH client. So when you run it, it may not run, looks like it's not going to run. Okay, this is Windows trying to save me by blocking the running. I have to right click and go to properties and then unblock. Sometimes when things come from the internet, Windows decides to block it as dangerous and won't run it. Now it runs. This is what PuTTY looks like. You give it the name of a server to connect to, and it will connect. I'm going to give it one of mine, ad.samsclass.info. You could give it any open SSH server and say open, and now it prints this message, login as. Then I could give it a name and a password and use my server, but that's not interesting. That's not what I want to do. What I want to do is modify this program and change that message, just so we can make a change we can see. So let's open PuTTY in OllyDbg. OllyDbg is here, and you can open any file in here and launch it. So I'm going to open, I'm going to go to my documents, where I made the one called PuTTY2, and here it is. Now, what debuggers do is they load the program, get it ready to go, and then pause. The way it works is here's the actual binary structure of that program, 6A, 6B, 68, 088. Those are the bytes that make the instructions. Here's the instructions, push 60, push something else, call a subroutine, move things into registers, call more subroutines, and so on. Here's the same old registers you've seen before, EAX, the stack pointer, and the base pointer for the stack, and the extended instruction pointer. So this is the assembly code that runs the program. These are the registers. Down here is the stack. So the stack contains this return value, and then it contains other values down here that are used by PuTTY. This is the series of stack frames that we got here by starting from Windows, launching PuTTY, calling a subroutine, calling another subroutine. This is that memory. And here's just a hex dump of any part of memory you want. You can dump anything in here you like, just like the bottom pane of Wireshark. It just shows you hex and ASCII of data. So when you load something in Olly, it is not running. It's paused. Let me see what this chat message is. Are you archiving this? Yes. Yeah, this should all be saved on YouTube. Good. All right. So down here in the corner, it says paused. That's your clue. PuTTY is not running. It's just letting me look at it. I have to hit this run button to run it. And now it says running. And since it's running, it has opened the window. So now I could run PuTTY here. Now, I would like to find the code that prints that login as message. So in my upper left column, I can right click, upper left pane, and then search for all referenced text strings. This is like strings, but again, like IDA, this is smarter than just the strings utility or BinText that just looks for a series of bytes. This looks for actual strings that are in fact used by the code, pushed on the stack or otherwise used. So these are strings that are actually in use. Now it's pretty hard to see. Let me make that bigger. Let's go font to this bigger font. Okay, so here's a lot of strings. And notice, by the way, that I'm in the module PuTTY2. Let me just point out something before we continue. If you view memory, you can see the memory that is used by the program. And I'm going to change my appearance to make this big. All right, so here we have, here's PuTTY. PuTTY has a text section, a data section, an R data, and a resource section. And I really only care about the code in PuTTY because I'm hacking PuTTY. There's a lot of other memory segments used by other things, like parts of Windows. If you, and the kernel and so on, here's the libraries that are used. And so if you don't run the code until you're in PuTTY before you start searching, you're actually searching the text strings in the Windows kernel or something, and you won't find them. So pay attention to the text string top here that tells me I'm looking in PuTTY2.txt. That's where I want to be looking. So now I'm going to look for login as. So let's go up here and find, which is, where's my find? Control F perhaps? No. Let me go to my instructions. Okay. This is how we got to here. And I wanted to find all reference text strings, search for text. Right click and search for text. Okay, right click, oh, there it is, search for text. Okay, log in as. I don't need it to be case sensitive, I search. Okay, here I found a login as 417053. I'm going to put a breakpoint there with F2, and I'm going to search again because in fact there are two of them, and it's not immediately obvious which one of them is the one that's used. So if I press F2, it turns red and puts a breakpoint there, and that means I can see which one actually does the printing. So now if I go to my PuTTY, which has been running all this time, and I put in the name of a server, like ad.samsclass.info, and open, it now is ready to print that message. It popped up the black box and stopped, and I can now see where it was. This is the one that is about to push a value on the stack, and if I make my pane a little wider here, you'll see it's pushing a pointer to log in as on the stack. Then it's going to call a subroutine which will print it. So this is the one that actually prints that message at this one, 41CB6E. I needed to find that because this is the code I wish to change. So I'm going to remove my breakpoints because I don't need them anymore. I'm going to view breakpoints and just delete them. Right-click, remove, right-click, remove. Okay. Get rid of this window and maximize the CPU window to get back to normal. Now, I would like to modify this code. I can right-click assemble. And here's the actual instruction that is being executed here. Push 467C7C. Now, let's not change it yet. Let's analyze it a little further. 467C7C, I would like to view that right here in the hex dump. I can right-click and I can follow in dump immediate constant. So it will find the address of this instruction, the address used in this instruction, and follow it. So it puts 467C7C down here, and I can see indeed login as colon, followed by a couple of nulls to terminate the string, then the other things like SSH login name, successfully started encryption, and the other strings are here. So this is the string that is used to be printed in this message. So if I change this address from 467C7C to 7D, it'll skip the L. So I'm going to do that. A very simple change just to prove that I'm in control of this program. So I assemble and change the C to a D. Then I hit assemble and then cancel. And now this turns red. The 7C is changed to a 7D. I've changed 1 byte. And now this says login as instead of login as. Now I'm going to save my changes. It is very difficult to save your changes in Olly. It took me about a year to get it straight. The thing is, Olly is too low level. You can save changes, but you can only save the changes in one segment. Remember, there's a text segment with instructions, which is the one I'm modifying here, and this is the data or our data section. I changed the text section, so I have to right-click here and copy to executable all modifications. This is confusing. It doesn't mean all the modifications you made, it means all the modifications you made in that segment. If you change data in 2 segments at the same time, you won't be able to save it in Olly as far as I can tell. So I copy all, and it creates a new file here called PuTTY2, and I can save that file and change the name now to PuTTY3. Okay, and save. Now, let's go try running that modified file. So I'm going to go, I think, to a command prompt where I think it's easier to see. Go to Documents, and then dir. Okay, so there's a file here called PuTTY and PuTTY2. Those are exact duplicates. There's a file called PuTTY3, which is exactly the same size, but I know I've changed 1 byte in that file. So if I run PuTTY3, it launches, and if I give it ad.samsclass.info and say open, it now prints login as instead of login as. So I've now been able to modify a file. Now, remember that security measure, how Windows didn't want me to load this because it came from the internet. Not only does Windows have that security measure? It also has a security measure called code signing, which should have prevented what I just did. If I take a look at the original unmodified file and go to Properties, there's a tab here called Digital Signatures, showing written by Simon Tatum. And if I look at the details, it tells me the signature is okay. So that's the original file, and the signature means it hasn't been modified. The PuTTY3 file, which I just made, has been modified. It still has a Digital Signatures tab, but I have to click Details here, and then it will tell me the signature is not valid. Now, I do not understand Microsoft's thinking here, which is very often the case. It knows this file was modified and broken, and it just let me run it. It didn't complain. It didn't pop out a message. I don't know what the point of a signature is if you don't enforce it. But that's where we are. Anyway, I give my students, not in this analysis class, but I give my students homework where we just put real malware in there, remote control clients in on top of the signature and run it and take over machines through a modified PuTTY. So I don't know what they were thinking about when they put that signature on there. Didn't do them any good. Anyway, so that's Olly, and there are some more fun things to do with Olly. I'm just going to show you another game to treat here. Here's the one where you add Trojan code. In fact, I think I'm going to just talk about these next two and not demonstrate them live because the kernel debugging is more important right now. But here you can add Trojan code. So you use this program called LordPE that lets you add another section to the code. And so you can see the existing sections like text, RData, and data, and add another one, which will be newsec. And you can just put malware in the new section and edit it to run that malware. And so that's here. And here's malware I generated with Metasploit. And you just put it in the new section, and then you make a remote control client, where it will start a listening port and anybody can take over the machine that's running the modified PuTTY. And here's a series of EXEs to patch that I got from the EasyCTF, captured a flag. Here's a funny game that's very easy to see in Olly. If you load this, it asks you for launch code, scans a number, and you either get it right and get an answer, or it insults you by saying, my dog figured it out before you. So you can read this code and try to figure out what the password is. But what's more fun is to modify the code. So in this case, you do a little bit of reading assembly code. So here it is. It calls puts. Like I say, always think like a small child. Find the easy part. On the right are nice names of things like readable strings and the name of C, normal C functions like puts and scanf and printf. So just read that. So here it prints a message. Here it reads something. Then it does some kind of comparison and a jump if something is not 0. And then it does one of two things. It either says you got it or it insults you. So what would be simple would be to just take away the comparison and take away the jump not 0, so you always win. If you remove these two instructions, then you will always win. So that's just filling them with nops that do nothing, no operations. And now when you run the patch file, any password will be accepted. And so in the same spirit, you can patch a bunch of these. And in the original one, you had to patch 67,000 of them. I made one where you have to patch 256. So you have to write a Python script to patch them automatically and harvest the results automatically. And it's kind of fun. But the last thing, before we run out of time, is kernel debugging. So the kernel is the high privileged part of Windows that has the ability to interact directly with hardware. So that's where all the hardware drivers have to be. Now, you could debug the kernel with WinDbg, the domain debugger Microsoft uses. The problem is you need two machines to do this. Because if you were to, say, put a breakpoint in the kernel, the way we just did with PuTTY, and try to stop it, when the kernel stops, the whole machine stops. It can't pop up a box or respond to the keyboard or anything. So you can't have one machine and debug the kernel. But Mark Vrasinovich, the expert again, you had to have two machines connected with a cable. He invented this thing called LiveKD, which does a kernel memory dump and lets you view the memory dump. So you can do some degree of debugging of the kernel with only one machine, which is bloody wonderful. Now, you cannot put a breakpoint and pause the kernel, but you can at least look at what the kernel is doing, and that's enough for a lot of good things to happen. So you just run livek kd -w, and it will launch WinDbg, and I just say No, don't save information. All right. Now it loads something. Gives me error complaining about modules, but it works. This launches this thing called WinDbg, and WinDbg lets you see the kernel. WinDbg is one of these very strange Microsoft utilities that's really a command line utility, but they put it in some windows just to get in the way. Anyway, you have to learn these commands, which are easiest to learn from the help page inside here. And the first one I'm going to do is bang process. Bang process. This gives me a list of the currently, it tells me what process I'm in. And the process I'm in is WinDbg, which it will show me someplace here. A session ID 1, process environment block, there, image, WinDbg.exe. This is the kind of information Task Manager would have shown. If I want to see all the processes, it would be bang process 00 to see a list of all the processes the way Task Manager would do it. There, this long list of processes showing SVC host and Wireshark. Oh, it looks like I left Wireshark running, or Wireshark crashed and didn't close properly, which is pretty common. All right, .help gives you some online help. .hh gives you much better help in this old-fashioned WinHelp file format. This is the help page that really tells you how to use WinDbg properly. So you can now list modules. Modules are pieces of the kernel that are running. So if I do lm, it shows me the kernel running modules. Here's unloaded and loaded modules, and there's a long list of things running in the kernel. And let me see. All right. All right, here we go. Notice this one is ntdil. ntdil is the kernel itself, also called NT. You can spot it from this long symbol path. It is not very big. Like all my ntdils goes from 775 to 776. Those are all the NT routines in the kernel. All right. And there should also be one called, here's the one called NT. That goes from 81 to 81. This is NTOS kernel. NTDIL, sorry, that's a DIL used to control the kernel. This is the one I wanted, NT. 81A to 81D. That is the whole kernel, the part that runs with maximum privileges. And I can now view things with DA and DB. So if I want to view the Windows NT, probably the simplest one is DB. DB will show me both ASCII and binary for the module NT. And so I get a dump, just like the one we were seeing in the dump pane, or you might see at the bottom of Wireshark. Here's the addresses, here's the raw hexadecimal value, and here's the ASCII values. And you should recognize this. This is a portable executable file, starting with MZ, and then having this message, this program cannot be run in DOS mode. This is the NTOS kernel.exe. The kernel of Windows is an executable file, just like everything else. And it copies directly into memory from the hard disk, just like every other exe. So that shows me the start of it. And now, X examines for symbols, so I can now find named symbols in the kernel with X, NT, bang, star. This will find named objects in there, in the NT, with any name, and I get a long, long list of them, and these are the Windows system calls, all of them. I'll go back. So things like quantum end and control halt device, and open enlistment, and so on. These are things that do things inside Windows. There are hundreds of them. Everything Windows does involves calling these little functions. So if I want to find the one that creates a file, I can do NT bang create or create file. So let's try create star, and I get a few entries here, create file info, create mini, and so on. Then if I'll put a star before the word create, I'll see some more. Okay, and if I want create file, it's star create file star. And now I get a relatively modest list that's not too baffling of things that are associated with creating a file, such as ntCreateFile, which is a routine that just simply creates a file. All right, I can unassemble that function with U, and I can see the code that runs it. So I can unassemble ntbang ntCreate file. And now I'll see the first bit of the code in this file, APFF55, move something here. That's creating the stack frame to let it run. If I want to see more of it, I can use the menu bar and view disassembly. Now, there's my menu bar. I was looking for that earlier. All right. So it's view disassembly. That opens a window that is intended to make it easier for me to see things here, although I find it pretty clumsy. You can scroll through things more or less here, sort of a page at a time. It's pretty clumsy, but you can view things there. All right, and what's more interesting is look at a driver object. This is how people have learned how Windows works, even the parts that are not considered public information by Microsoft. You can look at a driver object. This will show you what Windows drivers look like. So let me find my entry line, which is over here. Okay, let's close this extra window. All right. And in fact, now that I've found this, which was not present earlier, I can make my font bigger. I'd like to make my font bigger. How about you let me have something sensible like Lucida? All right, there we go. Hopefully less irritating now. NT driver object. There. So this is a series of things you'll see in a driver object. You'll see a string for hardware database, and there'll be a thing called friendly name. I need to make my window bigger to see it. Driver start is a pointer in here. There it is. That's the pointer to the code that runs the driver. And there's other information here about drivers. So you can figure out what's going on in Windows using NT, this debugger. And so you can disassemble the beep and see how it works. And that, now that you've done that, the last thing I want to show you is SSDT hooking, which is how rootkits work, an old-fashioned kind of rootkit. So here, this is the SSDT. Let's open it first and then I'll talk about it. The KI service table. Okay, should be pretty visible at this font size. Okay, this is a series of functions, and what's going on here is the left is counting up 4 bytes at a time. This is the actual address of this entry. This is the data that's in the entry. So there's a series of pointers, and the pointers point all into the kernel. They all point to 81, because remember, my whole kernel starts with 81. It's not very big. It goes from 81A to 81C is the kernel. So if you want to call a NT system call, like this one, NT alert thread, your code does not directly jump into the kernel. Your code calls an offset table in your own code, created by the compiler and the loader, and then it calls the SSDT service set descriptor table, which then points to the kernel. These 2 layers of interaction are really important because you might update your compiler and recompile your code and move where things are, and you want to still find the operating system code where it belongs. And Microsoft might want to patch the kernel with the system update and move these routines around, and your code that was compiled previously has to keep running. So your code never jumps directly to a kernel routine. It jumps to this lookup table. And if Microsoft has an update, they also update the address in the lookup table so your code can find the routine. This is good, but it also creates a vulnerability because this is how rootkits work. You just change this address, and now every time someone tries to do something like open a file, it runs off to open my malware first instead of opening the file. And not only did malware do this, but all system files did this too. Here's a program I found. Somebody practiced this using SSDT hook that made a few hooks that are relatively harmless. And then I wanted to find some malware to analyze, but there wasn't any malware in that malware analysis book that did what I wanted here. So I found some good malware called Zonalarm. Like I say, a few years ago, every honest legal security product used this terrible technique, and it really annoyed Microsoft. They really don't like everybody messing with the SSDT without their permission, but this is how they all worked. So if you install ZoneAlarm, ZoneAlarm will put a bunch of fake entries in the SSDT, and they're easy to spot because they'll have a value that is wildly wrong here, not starting with 81. And so here's an example of what SSDT looks like with that SSDT hook in it. You have 81, 81, and then a 94 and a big error message, then 81, 81. This is what happens when you hook the SSDT. Now, fundamental kernel routines that should be running Windows are jumping into user land, doing God knows what instead of what they should be doing. And that's how malware does it. That's how antivirus products have been working, and other products up until a few years ago when Microsoft really got fed up with this and started having better ways to do it. Microsoft tried to lock all the antivirus companies out of the kernel completely, but they threatened to sue for antitrust violation, and they've been going back and forth with different ways for them to somehow protect your system without breaking Windows too much in the process. Anyway, that's where I wanted to get you. We've got a few minutes left. Let me see if there are any more questions coming in. Looks like there aren't. So that is all of the stuff I had ready for the malware analysis. I've got a couple of minutes left. I just want to show you one more thing on a completely different topic, just because I think it's wonderful. Laura Chappelle, who teaches Wireshark all the time, I went to a talk by her, and she showed me how to get DTN working, which I've been wondering about for years. If you go to the Deep Space Network, you can see this thing live. I thought if I had a few minutes, I'd show it to you now. Yeah, okay, that's right. Here's a malware question. How does anti-malware work today and the new Defender kernel? I do not know. These are very good questions, but I don't know about that. There's a new Defender kernel level. Yeah, I'm not sure. I don't have anything valuable to tell you about that. Anyway, this thing here, you can see the protocol used for deep space communications here, and I thought it was very nice. So you can see it live here, and you can set it up on your own machine. This is called Delay Tolerant Network. Vint Cerf wrote it a while ago. It's an approved protocol. And so you can actually set it up and run it between a couple of your own virtual machines, and you can send it up to my server and get on Winter's boards with this stuff. So you can configure these semaphore arrays that send data through unreliable channels. And so I thought I'd mention it. It's from my homepage if you want to do that. Right up here, Interplanetary Overlay Network. I've heard about it for years, and I just learned how to do it. Anyway, I think that's it. I have a few minutes if there are any more questions, although I'm not having much luck answering the questions. Okay, people are saying thank you, which is nice. All right, I hope this helps you. And I don't suppose it doesn't look like too many people are doing it live during the talk. Let's see if anybody's getting on the scoreboard. If I go here and here, yeah, just a few people are doing it live, but you know, it's only 2 hours. So, but this will stay up and you can do it later if you want. A lot of people have done it in the past. As Cheerio was saying, if the people who have done this before are here, DEFCON in China, B-Sides in Vegas, DEFCON in Vegas, CactusCon, various teaching conventions, lots of people have done this. And you know, it's just a way to trick people into doing their homework by making it a little more fun. Someone is asking for book recommendations for Windows on low-level kernel. Yeah, that's a good question. But you probably, I think the best one is Mark Russinovich. See if I've got it in my, I don't have links here. Let me find it. Mark Russinovich, Windows, has a book on Windows system internals. Pretty sure that is, let's go to Russinovich. He's the guy, world's expert on Windows internals with Russinovich. This is the Bible of this business. Mark Russinovich wrote almost all the tools you've been using, and he is the guy that does it. He also writes these James Bond type thrillers and pretty much lives a life like that. But anyway, that's it, Windows internals. That is probably the Bible of this stuff that will tell you what's really going on in there. Yeah. a 64-bit debugger like Olly, I would use Immunity. Well, no, does Immunity do 64? I know some people like x64 debug. I don't think I've done 64-bit debugging like Olly on Windows. It's a good question. People say use WinDebug and just get used to it. It's kind of annoying. I don't know. It's a good question. I've got a lot of x64 debug. Yeah, that's one I've heard people say. It's probably the best of the bad lot. All right. Any others?
I actually have a question.
Yeah.
When you're working through IDA Pro, I actually put it in the chat, you might have missed it, but when you see offset, can you assume that you're getting close to reversing the malware?
Offset?
Yeah.
Well, the offset is just a location of, no, that's a location of address.
Okay.
All the offset, that could be referring to any kind of stored value. So it doesn't necessarily tell you much. That's the problem with IDA. It is sort of baffling and it's not obvious when you're making progress. That's why dynamic analysis is much more fun because you can see something happen and you know what's going on. IDA, you very well spend all day studying something and then discover that it was something utterly boring, like you have to see what version you were doing.
Okay.
That's why IDA has a real steep barrier learning curve to getting in. When you're new at IDA, you'll waste a lot of time and not get very far. Am I going to be at Circle City Con? Yes, I'll be there. I'll be teaching a lot of this stuff live at Circle City Con. In fact, I have to send them my list of classes. I'm going to do, maybe not this workshop, but several workshops like this there, including Red versus Blue, which is live head-to-head combat. I've got that working, and I'll definitely be doing that at Circle City Con. Okay. All right, are there any others? Well, I guess that's it then. Oh, Cheerio, one more, okay. Something coming in? Oh, she said she's offering a chance for one more question, but perhaps nobody's doing. Oh, Radare 2 or Cutter GUI instead of IDA. Yeah, Radare 2 is nice, although I've never seen it on Windows, just Linux. And I found GDB to be just as good. Cutter I haven't used. I do know Hopper, which is very good for Linux and the Mac, but not for Windows as far as I know. Radare 2 with Cutter GUI, I haven't tried that. Oh, it's part of Radare. That's a good question. I didn't get much good out of Radare. I tried it a few times. It seemed too much bother. And I've seen a lot of attempts to put a GUI on front of GDB, which I think is what Radare is, and most of them are just in the way. But it may be possible to do some of these things there. There are a lot of disassemblers and debuggers, and they, of course, each have their virtues and proponents. All right, well, I guess that's it. I guess I'm going to go. Good luck, folks.
Hey, Sam, can you hear me okay? Thank you so much, everyone, for coming out, and thank you so much, Sam, for taking the time to do this. I sent you a little message on Twitter, and yeah, thank you, everyone. And have a good night and Happy New Year.
Okay, farewell.